Hi everyone, I'm recording this video to show you my solutions to homework 6. Well, but I need to, I recorded this video early, but I have to post this video after the due date of the late submission. So, when you see that, and then it should be the Tuesday of the last week. Okay, so let's see the questions. So the first one, we have an adjacency list representation of a graph and with the V and the E. So V is for the nodes and the E is for the edges. And then we have we need a O V plus E algorithm to build an adjacency list representation of the equivalent undirected graph. But we want to remove two things. So number one, if there are multiple edges between two vertices, and then we want to only keep one of the edge. And then if there are self loops, and then we want to remove that. Okay, so before talking about my solution, so how if we have a graph, and then how do we have multiple edges between the same two nodes? And say, for example, we have the node A and node B. So for the node A, and then the adjacency list, we have the B and B. And then what does this mean? This means that from the node A, and then there's one path that we can go from node A to node B, and then we have another path that we can go from the node A to node B, right? So from A to B, there are two possible paths. Okay, and then the other one is, how about the self loop? A self loop means, a node goes to itself. Say we have a node C, and then for the node C, it is connected to node C again. So in this case, and we want to get rid of such cases. Okay, so the process will be similar to how do we do the checks. So on the multiple edges between the two same nodes, and then we want to keep a record on from node A to node B whether there is already a path going from node A to node B. If there's no such path, and then I want to keep the B. And then if there's already a path that goes from A to B, and we know that, and then for the second B, we want to say, okay, I don't want to take you into my adjacency list again because there is already a path from A to B. So this B should be removed. And then how about self loop? Well, that is easy because I know, I'm recording the edges from node C, right? And then, if we see, okay, the target node is also C, and this means there is a path or there's an edge from C to C itself. So we want to get rid of that. Okay? So, and then for my algorithm, and I does the two things. So, for each of the node I'm holding, and then I want to visit all the adjacency edges, so adjacency nodes, and then I want to check two things. So if we want to see, I want to create a set, and this set records what are the adjacent nodes, and I have already know from the current node U. And then if we have a V that node U is connected to, I want to check if this node V is in my set or not. So here I'm using the data structure set in Python. And if you want to use a hash table, that is fine too. So if this V is in my set, and then that's good. And then if this V is not in the set, and then if this V is not U, so and then I want to add this V to my set, and otherwise I want to ignore that. Okay, so this is the process of my algorithm. And the key is here you want to use either a Python set, or you want to use a constant time data structure to check whether you have this V in your set or not. Okay, so the next one, we are doing the undirected graph below, and then we want to get the D and V for doing a breadth first search. Okay, so for breadth search and breadth first search, and then we are starting from the 3. So the 3 will be black. So once we have the 3 as a black node, and then we have already seen the node 1, node 6, and node 7. So in our queue, we have the node 1, 6, and 7. And then, well, for the node 1, and we know the parent is going to be 3. For the node 6 and node 7, and then the parents are 3, 2. Okay, so the next round, and we want to visit the node 1. So the node 1 is going to be black, and we see node 2. So for the node 2, now we know the distance from the node 2 to the source, or from to the root, is going to be a 2, and the parent is going to be a 1. So 1 is black, 0 is black, and now 2 is gray, and 2 is in the queue. So the next one, we are going to visit 6. So when we visit 6, and then we see the node 5. So the node 5 is going to have the node 2 as a parent, and then the D for the distance from node 5 to the root is going to be a 2. Okay, and then the next one is going to be a 7 in the queue. So we pop 7, and 7 becomes black, but there's no new nodes we can see from the node 7. So the next, we are going to visit the node 2 again. So for the node 2, from node 2, and then we can see node 4. So the node 4 is going to have the parent node 4 is going to have the parent as a node 2, and then well, node 2 becomes black, and then we have the node 5 and node 4. So we visit node 5, nothing to explore, so node 5 becomes black, and node 4 becomes black too. Okay, so this will be the final word. Okay, so the next question. Well, if we are running the BFS, and then instead of doing a adjacency list, if this graph is represented by a adjacency matrix, what will be the changes we have to make, and then what is the time complexity of this algorithm? So this is the algorithm, and then if we want to change this version to adjacency matrix, and then what are the things we want to change? So well, if this is my new version, so for this part, and then well, we are trying to visit all the nodes, and then for each of the nodes, I want to change the color to white. So this color is going to be an array, so this will be a linear to how many nodes do we have. So this is going to be an OV. So 1 to 4, that is OV. And then from the 5, 6, 7, 8, 9, and they are all constant time. So 5 lines of constant time. Okay, and then while queue is not empty. So how do we know how many runs do we have to iterate in this queue? And the answer is, for each of the nodes we are going to put it into the queue, and then we are going to pop it from the queue. So there is guaranteed that we are the line 10, this outer iteration is going to run for v times. Okay, so now we have to figure out what is the cost for the body of the outer loop. That is the cost from the line 11 to line 18. Okay, so for each of the round, we want to dequeue one of the node, and then for each of the for the node we have already dequeued, which is the node U. Now we want to visit all the adjacent nodes. Okay, so if we have a adjacency list, and then we just go and then using the U, and then we can see what are the adjacent nodes do we have from the node U. But what if we have a matrix? So if we have a matrix, so node U represents a certain line in the adjacency matrix. And then let's assume that the node U is 0. Okay, so from the node 0, and then we have to check, okay, on the adjacency matrix 0, 1, and that is we are checking if the node 0 is connected to node 1. So we have to check that. And then we have to check the value on the index 0, 2. That is, if the node 0 is connected to node 2. And then we have to visit all the values in this adjacency matrix. This will give you a linear time. Okay, so the key here is for the line 12, and then we have to visit all the possible nodes and check in the adjacency matrix and see if this node is connected to node U. So this will give you a linear. So line 10, you have a linear to how many nodes do we have? And then on line 12, because we are using a adjacency matrix, we have another linear to how many nodes do we have? So it is a linear v inside another linear v. So this is gonna give you a O v square. Okay. So the next one, we are doing the DFS. So from the node Q. So DFS, and then, well, the process will be, we start from the Q, which is the root, and then we go down, we go down, we go down. Well, we go down until there's no further ways to go, and then we step back, and then we see after stepping one step back, is there any other nodes we can go? And if not, we step back again. Okay, and then for each of the node, we record the time that we started visiting this node, and then we also record another time that we decide, okay, there's nothing more we can visit, so we step back. So we are recording 2 times for each of the node. So we're starting from the Q, so this will be a 1, and then S, and time will be a 2, and then we go deeper, and then we have the V, and the start time will be 3, and we visit W, and then the start time will be a 4. So after W, and we find, okay, we can go to S. But this S has already been explored. So from W, no further nodes we can go. So we say, okay, we put W as a finish time as 5 and say, okay, W, we finish at 5. So we step back to V. So from the V, no other place we can go, so we finish at 6, and then we go back to S, and then from the S, no other nodes we can go, so we finish on 7. So finally we go back to Q. So do we want to put an 8 here? The answer is no, because from the Q we can go to the T, right? So we go down and then we visit T. Okay, we started T at the 8, and then we start the X at the time 9, and we started Z at the time 10. So okay, from the 11, from time 11, we find, okay, Z, there's no further nodes that we can visit, so Z stops at the time 11 and X stops at the time 12. So how about here? So we step back to the T. So do we want to put a 13 here, saying we finished the T at the time 13? The answer is no, because we can go to the Y. So we go to the Y, we start at the 13, but from the Y, we can only go to the Q, but this Q is already explored. So from the Y, no other place we can go, so we say, okay, why we stop here? So we stop at 14, and then we go back to the T, and then we stop at the 15, and finally at the Q we stop at 16, because from the Q we can go to nowhere. But you can see from the R and Q, R and U, they're not finished. So we are gonna here start visiting R at the 17, and then 18 we visit U. So we finish visiting U at the 19, and we finish visiting R at 20. So that's it. Okay, so after this version, so all the red edges, they are the 3 edges. And then what about the other ones? So from the Y to the Q. So Y to the Q. So Y is well a tree leaf, and then it's pointing back to the root of the tree, so it's going to be a back edge. And then W to S again, because the tree edges are Q to S, S to V, and V to W. So now W is a leaf node, and then W to S, W is pointing back to the grandfather node, which is S. Okay, so S to V is a tree edge because it's part of the tree. And then R to Y. So R to Y, that is a cross edge because R and U, this is a subtree. And then Q, Y, and Q, T, X, Z, and Q, S, V, W, they are another subtree. So that is from the R to Y, that is from one subtree node to the node from another subtree. So this is a cross edge. Okay? Okay, the last question. Well, for the Prim's algorithm, and I'm assuming that we are going to start from the node 0. So in the first round, and we only know the node 0, and then the key is going to be a 0, and then we don't know other nodes. So in the priority queue, we only have the node 0, so we expand the node 0. So we expand the node 0, we see there's a node 1, node 3, and node 4, and the cost for those three nodes to join the MST is 3, 8, and 7. Okay, but so far in our MST, we only have the node 0. Okay, and then in our queue, we have three candidates we can pick and then include that into my MST. So this 0 is in my MST, and then well, we can include the node 1, the cost is a 3. We can include node 4, the cost is 7. We can include node 3, the cost is an 8. So we want to go for the lowest one, so we want to include the node 1. So the next round, we want to include the node 1 into my MST, and then, well, after we have the node 1, we want to update the nodes, then we can visit through the node 1. So we have the node 2 and node 3. So for node 2, well, this is a new node, and then we say, okay, for the node 2, if you want to join the MST, you can go through the node 1 and the cost is a 1. And then for the 3, it has to be updated because we used to know that 3, if you want to join the MST, you can connect to node 0 directly, and then the cost is an 8. Now, because node 1 is also part of the MST, so we can say node 3, if you want to join the MST, you can connect yourself to node 1, and then the cost is going to be a 4. So we also want to update the cost here. Okay, so now we have the MST members 0 and the 1, and then we have three candidates. We have the node 2, the cost is 1. Node 3, the cost is a 4, and node 4, the cost is a 7. Okay, so we pick the cheapest one. So we have the node 2 included into my MST. So because I have the node 2 included, so now in MST we have three nodes 0, 1, and 2, and then, well, we have to update the 3 again because 2 is now a member of the MST. So for 3, if you want to connect yourself to my MST, well, there is a even cheaper way. That is, from the node 3, you connect to node 2, and the cost is going to be a 2 here. So and then in our priority queue, the node 3 now has the cost to be a 2, so we want to visit the node 3. So after we have the node 3 included in the MST, so now the MST we have 0, 1, 2, and 3. So, and then for the node 4, because node 4 used to have the key to be a 7, but now because 3 is a member of the MST already, so we want to update this value. So it will be a 3, and then, well, you can join the MST using the cost of a 3, and then the parent will be a 3. So eventually, at the last round, we want to expand the 4, and then nothing got updated. So this version is going to be the final version of the key array and the pi array. So eventually, if we want to highlight all the edges of the MST, and then this is what we have. Well, it is a little bit strange because, well, this MST is just a one sequence of the nodes. So 0 to 1, 1 to 2, 2 to 3, and 3 to 4, and this is my MST. Okay, so that's it, and I hope this video helps you prepare for the final exam. And by the way, there will be another video showing you a sample final exam question. Okay, bye bye.